In the project, we are going to study about the sampling of images and image processing. We could load images into MATLAB by using the imread command. Images will be turned into a m times n matrix for black and white images, or m times n times 3 matrix for color images. The m and n represents the width and height of the image, and there will be total m times n pixels for this image. And please notice that the numbers stored in this image corresponding matrices are in the format of uint8 rather than double or floating point numbers. Numbers in the matrix determines the intensity at the specific location of the picture, which is also the position of this number in the matrix. For all images, the number is in a range between 0 to 255. For black and white images, 0 means fully black, and 255 means fully white. For color images, the 3 layers of the matrix are corresponding to the 3 base colors, red, green, and blue. This is consistent with science that all colors could be represented by different combinations of ratios of these 3 base colors. The first layer is for red, second for green, and third for blue. The numbers in this 3D matrix also determines the color intensity of the specific pixel. 0 means no intensity, and 255 means full intensity. And in MATLAB, we can adjust only one color for a colored image by simply changing numbers in the corresponding location and layer. Image processing in MATLAB is not hard to understand. Information contained by the image was turned into matrices, and pixels were measured as intensities and be stored as numbers. Thus, a change on pictures simply means a change of these numbers. This is kind of similar to what we learned in DSP class, that we deal with continuous time signals by first converting them into discrete time signals, and then compute them in discrete time, and finally convert it back to continuous time. And here, images would mean continuous time signals, and matrices would mean discrete time signals. For example, enhancing contrast means making bigger number getting bigger and smaller number getting even smaller, so that the contradiction between high and low intensities has been significantly increased. And blurring images, like for confidentiality purposes, is simply destroying the order of the specific region. And this is achieved by randomly changing numbers of the matrix which correspond to the specific area. And this could also apply to noise cancelling of images. Noise means disordered numbers in the image matrix. Their intensity would be abrupt compared to adjacent pixels. So, by writing a proper algorithm that could find out and adjust these abrupted pixels, the noise of image could be cancelled. These are only 2 potential applications of sampled images in MATLAB. There could be other applications based on the sampling theory of images, and in our project, we deal with black and white images only, since color images have 3 layers, but black and white images only have 1. So it would be easier to compute with, and our example would be the Rutgers EE building in Bush campus.
Okay, let me introduce how our MATLAB code can implement our target. For sampling, first we use image read function to convert the image information into matrix for storage, since the image is RGB 3 colors. The information obtained is 3-dimensional, so first we use RGB2 gray function to convert the image into a 2-dimensional grayscale. When do sampling, we use our matrices to sample the values of the original matrix at the interval 2, 4, 8, 60, 32. The number of sampling points continue to decrease. The displayed image become more and more blurred and finally tend to more suck, which also shows that sampling the more points, the better the image quality. For quantization, when we do quantify, call hit EQ function to change the number of grid levels of the image to achieve image quantization on different levels, and use image heat function to see how the grid level change. Through the comparative analysis on different quantization levels, it can be found that the quantization becomes lower and lower. The details of the picture become less and less clear and detailed, and the effects of the picture become worse and worse. Next, we will try to do random non-uniform sampling. First, we build a sampling matrix with only 2 values, 0 and 1. Then we use bitwise multiplication on these 2 matrices. Compare with the initial image, we found the resampled image almost represents the details of the original image, but it is dimmer than the original one since we just do random non-uniform sampling. For the unsampled pixels, we just substitute it with a pure dark element. Finally, we try to do image enhancements, which include spatial domain and frequency domain. First, we try to do image smoothing using mean filter. The built-in mean filter in MATLAB can be implemented using the f-spatial params n function, where params represent the type of filtering and represent the template. Since the mean filter has a better effect on Gaussian noise, the image of Gaussian noise is smooth. The effect is as follows. Based on the principle of mean filter, we wrote a piece of equivalent code. The effect is, it can be found that except that the running speed is slightly slower, the effect is the same as the functions that come with MATLAB. Then we try to do median filter. The median filter that come with MATLAB can be implemented using median filter 2 INN function, where I represents the image to be processed and n represents the size of the template. Since the median filter has the effect on salt and pepper noise, the image of salt and pepper noise is smooth. The effect is as follows. According to the principle of median filtering, we wrote a equivalent piece of code. The effect is. Then we try to do image sharpening. There are many methods for image sharpening. The most common used sharpening operator include gradient operator, robust operator, pre-width operator, Sobol operator to calculate gradient. According to calculation principle of gradient operator, we wrote equivalent code. The code is, the effect is, MATLAB come with function of pre-width operator and Sobol operator. The code and the effect are as follows. In fact, it can be found that the difference between this type of operator is only in templates. So we just write down a code that can customize various templates, and we do verification with robot operator. After comparison, the effect is found to be the same, indicating that it is effective. At last, we try to do practical image sharpening with the Laplacian operator using our templates. After adjusting the parameter of the Laplacian operator, and the effect is. So we found that the age of the building, the trees, and so on, or on our sharpening image is become clearer than the initial image. So based on these results, we successfully do the image sharpening. The last part is about frequency domain enhancement, which includes high-pass filter and low-pass filter, and mainly use Fourier transform and inverse transform to process image. There is no direct filter function in MATLAB, but you can combine the principle with the mathematical formula in MATLAB to construct various filters. We constructed ideal, Butterworth, and exponential high-pass and low-pass filter. Using different type of filter, the effects are this. So in conclusion, it can be seen that the low-pass filter and can suppress image noise and improve the image quality. And the high-pass filter can highlight the boundaries of the image. So that's all the explanation of code.
Okay, during our research, we have found many interesting proper-nouns, which these proper-nouns are closely related to digital signal processing and digital image processing. What is more interesting, that this noun summarized our research process of the digital image processing to some extent. The first noun that we have met is sampling, which we are very familiar with. Sampling is a very important concept that we have learned this semester, and we all know that a continuous time signal needs to be sampled before it can be turned into a discrete time signal. But for digital image processing, sampling is far away from enough. So we continue to study the concept of quantization, which is also the basis of digital image processing. We quantize the signal into a digital signal for image processing. I can say that quantization is the very first step of image processing, so that some of the later operations are realized after this. The next is image smoothing. We have to deal with the digital image after the pixel is enlarged. The boundary of the image will be jagged after the pixel is enlarged and after increasing the pixel interpolation and the pixel resolution, make the image thinning that is smoothing. So in the duration of we studied the image smoothing, we also come into contact with two different filters, the main filter and the median filter. Firstly, we use the main filter to process the image, but we find that the edge of the image is destroyed. So we use the median filter to reprocess. The result is optimized, but we still cannot completely protect the edge of the image. In order to better deal with the image edges, we continue to learn about image sharpening. Image sharpening is an effective method of makeup for the image edge. Through this method, we can make up for the damage to the image edge in the process of filtering. If you look at this cat, you can find that I'm just citing an image from the internet, but this cat perfectly shows how sharpening works.
We chose image process as the subject for this survey project. Compute transfer the continuous time signal to discrete time signal for saving image. All image in digital world are three-dimensional array. We try to get more into the image process, utilize the knowledge we learned from this course. We deep look into some filter which will remove noise from image and make the image look more clear. We use something like mean, median, low pass, high pass, band pass, and uniform filter. During the process, we understand image process deeper. Of course, we made a lot of troubles questions during the we try our best to solve it. Firstly, we try some method to do image process like mean, median, frequency filter. They're easy for us to understand and to write the code because most they covered on this course. However, for uniform quantization are big deal for us. We search a lot of information and to understand how they work. For the quantization is about mapping the larger set into smaller sets. Its core is a compression algorithm, quantization error. We take a long time revise code to achieve our goal. Additionally, we also want to utilize the Laplace matrix to do image process. It can help us to find some useful properties of image. It can calculate the number of spanning trees, so it could use to construct low dimension. But it is complex, so we didn't solve it perfectly. And maybe if we have more time, maybe we can do it better. During this project, we learned a lot of things about image process. Thanks for this learning opportunity.